Welcome back. In this video, I'm going to talk a little bit about some strategies for how to match up multivariable functions with their graphs, because I understand that it can be kind of hard sometimes to visualize what these look like. So I just want to kind of highlight some strategies that I personally like to use to be able to identify key features in these. So a lot of this I just kind of based on my knowledge of what the two-dimensional version of these graphs look like. So a really good example in here is actually going to be like the cosine function. Because generally speaking, when we're working with like sine or cosine, we're going to wind up with something that looks kind of like a wave. Like that's going to be its predominant feature. And I mean, like, you don't have to, with these kinds of problems, you don't have to worry too terribly much about like the exactness of, okay, is it starting at 1? Is it starting at 0 or something like that? Because a lot of that's going to depend on what's been plugged into it. But the main feature here that you're going to look for is that it has a wave-like property. So for example, if we're looking at problems B, D, and F, you know then that it has to correspond to this graph, or this graph for those three, because those are the only three that are showing any sort of wave-like patterns in them. But that kind of just narrows down like some large-scale properties. How do we kind of fine-tune from there? So these guys are rational functions. And a rational function, you know, something kind of like 1 over x or whatever, maybe even 1 over x squared might be a better example for these, is they typically look something a little bit like this, where you have something that kind of, it's flat almost everywhere, but then it kind of comes to a point somewhere around like 0, or, you know, you divide by 0 and you wind up with a point out of it. So with these kinds of graphs, the overarching theme that you're going to look for is something that is kind of flat almost everywhere, but then comes to a point. So like for C and E, you're going to wind up with either A or E being those. So again, we've kind of classified the overarching patterns, but then how do we distinguish between them even further? So now we want to look at maybe what's been plugged inside of these guys. So when we're working with like the cosine, for example, so if we look at this, what's inside of it is an x and a y. So we know that we have waves from the cosine, and then we know that those waves have to be in the x and in the y direction, okay? So it's going to kind of split down the middle of those two. So that's something you're going to want to kind of keep in mind when you're deciding which one of the graphs this belongs to. In contrast, this cosine only has a y plugged into it, so the waves are only going to go in the y direction. And that should be enough to narrow down which one of these here is going to correspond to letter D. And then finally, if you look at this one, we know that we have waves. And this actually brings me to my next big property that you'll see in a lot of these. Anytime that you see x squared, y squared, you should immediately think of a circle, right? Because if we were in the xy plane, you would get a circle. So we have waves that are in circles. Okay, so again, kind of look at these three graphs that have the waves in them and decide which one of these waves are in a circular pattern. I think that that's probably pretty apparent which one's going to pair with that. And then from there, you can use a little bit of process of elimination to figure out the rest. Now, if we look back at C and E and how to narrow these down, well, we have this x squared, y squared thing in here. So we're expecting to see some sort of like maybe circular type property there. But notice that this one is missing the 9, whereas the x has the 9, and this has the 9 on both. The symmetry here is actually going to give us something that looks a little bit more like a circle. But anytime you see a lack of symmetry between the coefficients, like say this has been stretched by 9, and I guess this one's been stretched by 1, that means that it's been squished in some direction. Okay, so you're going to want to look for two graphs that look really similar, because these two are pretty similar equations, but you're going to want one of them to be kind of like a squished version of the other. And if you use all of these properties to kind of match up all of these functions, that's actually going to bring us back up here to A. By process of elimination, you can probably figure out which one that's going to be. But generally speaking, when you wind up with these absolute value functions, just note that the absolute value of x always has some sort of like V shape. So you're going to be looking for something that has a bunch of V shapes in it for that one, in case you're not able to get that from process of elimination. So that's going to be that one's main feature. So, but anyway, just kind of generally, I'm going to let you finalize what the answers of those are. But the big idea here is think back to what the two-dimensional version is of each of these guys and what their main geometric properties are, or like visually what they look like, and then try to see if you can piece those together, combine different physical or geometric properties of those to kind of produce an overarching picture of what you're working with. So hopefully that's kind of a helpful strategy for you. That's just personally what I use, and I think it works out pretty well. So thank you for watching.